Today, we are also going to talk about what is called thermodynamic balance laws and field equations. Okay, and you will see that the equations that we derive today will be useful in deriving constitutive equation later on. Okay, so thermodynamic balance laws and field equation. So this is the same thermodynamics that you guys have learned in your undergraduate. First law of thermodynamics, second law of thermodynamics. There is also zeroth law of thermodynamics, right? So we want to derive the same thing in the framework of continuum mechanics that we have been doing. Okay, so let me start with the first law of thermodynamics. And as I told you, the motivation is to come up with equations here which will be useful in obtaining stress-strain relationship. So does anyone recall what was the first law of thermodynamics? So it's that the heat supplied to a system plus the work done on a system, that's equal to change in internal energy of the system, isn't it? Yeah, of course, it's the principle of conservation of energy. So this is also called conservation of energy. So U here is denoting the internal energy of the system. This is the work done, and this is the heat supplied. Okay, and this law is for what is called quasi-static processes, where the kinetic energy of the system is very small. But if it's a dynamic system where the it's evolving and it has kinetic energy, then we also add here kinetic energy. Okay, so this is the first law of thermodynamics and its rate form. If we talk of its rate form, then it says that Q dot plus W dot, that's equal to U dot plus K dot. Okay, so that's the first law of thermodynamics. And you recall in the last class, we worked out power form of work energy theorem. And what we had seen is that the work done, W dot, that's equal to K dot plus some stress power. You recall? So this is also going to hold always. But when we talk of thermodynamics, we also include the heat. Okay, so let's proceed from here. Now this is for the entire system. This is for a system. Now our system, as you can recall again, we have some reference configuration which is evolving into the deformed configuration or the current configuration. And then we take a part of the body, which could be this, and that's your d ref, which in the current configuration is dt, right? It's occupying the region dt. So we have to now write this thing for dt. Let us write above equation for dt, and you see that has to hold for any part of the body, because any part of the body is also very much like a system. If you are following it, you know, d ref going to dt, if you are following the particles, then it's very much like a system. Okay, so Manoj asked, what is the convention for positive w here? So positive w is, you know, force f dot v, right? Or f dot displacement. If that is positive, then w is positive. So suppose we have a body and you are applying a force f at a point, and this point will undergo some displacement, let's say delta. So work done on the body is f dot delta, right? You take the product of force acting on the body dot with displacement of the point of application of force. So that's a total, that's a work done W on the body. Okay, and it's negative of the work done on the agent, then you can say. But on the body, it is force that is acting on the body dot with displacement of point of application of the body. Okay, so with that thing in mind, let us try to write this for each of the terms here. You have 4 terms over here. So W dot, let's first write W dot. What is W dot? So W dot is the mechanical work done, okay, by external forces. Okay, it has to be by external forces, because you have a system and Q being supplied externally from the external environment and W being done from the external environment. Okay, so I can also put some subscript here. So it's external, it's external. Okay, so heat supplied and the work done from the external environment to the body is equal to rate of change of internal energy of the body plus the rate of change of kinetic energy of the body. Okay, so let's write this now for each of the terms. So first of all, W dot. What is this W dot going to be? So this is something we have already seen. So we categorize the external forces into 2 types. One is the body force and the other is the surface force, right? And on this dt, we have traction T as the surface force and B as the body force, isn't it? So this then becomes integral, surface integral over del dt of the traction T dot V dAy, right? And then for the body force, we have volume integral over dt rho b dot v dvy. Okay, where b is the body force per unit mass, so rho b is the body force per unit current volume. So this is the W dot. There is nothing else remaining. What about Q dot? How do we write Q dot? So think of this dt here. Okay. In what ways Q dot can be supplied to the body? So there could be, heat escaping from the surface of the body, or this part of the body. Heat could be escaping from here, and which is also called heat flux, isn't it? Per unit area. Okay, Toiba is saying that we didn't use rho earlier. Okay, so we can drop it then. If we haven't used it, we'll drop it. It's just then B dot V, where B is now the body force per unit current volume. Okay, and it's a matter of convention. I was just looking at the book today in the morning, and they are using rho B, I guess. So if you use rho B, then B becomes body force per unit mass. It's a matter of current. So, but let's stick to what we have been doing. So B is the body force per unit current volume. Okay, so thanks for pointing it to me. Okay, so coming back to Q dot. So can you guys tell me what could be the sources of, in what way can heat be supplied to this part of the body dt? One is, we saw that heat flux. So you see that it's an internal part of the body. And then even from this internal part, heat may be going to the remaining part of the body, right? By means of conduction, for example, isn't it? So this could be by means of conduction if it's an internal surface. And if it were the external surface of the entire body, then it could be by means of convection, right? Okay, so bottom line, heat can be escaping from the surface of the body, or from the surface of the part of the body which we denote by heat flux. And what else? Heat could also be generating, just like the body force, which is the force acting on every particle of the body. There could be a heat source per unit mass, for example. To every particle, for example, when electric current is passing, then due to current, heat generates, right? If there's some resistance, then the heat generates, and that is at every particle of the body. So we can have a source of heat over the surface, and we can have a source of heat over the volume. Just like we did it for the forces, we can also think of the same for the heat. Okay, so let's denote the heat source per unit volume thing, or we'll say it as per unit mass, because that's what the textbook says. So it becomes small r. R is the heat source, SOURCE, heat source, and that's per unit mass. Okay, so rate of heat supply. So I should write here rate of heat supplied to the body. Okay, it is supplied to the body per unit mass. Okay, and this heat flux, the book denotes it by the symbol H. But you see that the heat flux, it is kind of going out of the body. In the book, they use the convention of heat flux going into the body. Okay, we will use a different convention, and this is something I think all of you have seen it also in your undergraduate class, and it also is used in several books. Unfortunately, different books use different notations, so that's a sad part. But then there are so many people, they can't be using the same thing, so we have to just accept it. So here we are saying that the heat flux is heat going out of the body, and this is per unit area. Okay, this is per unit area. So with that thing, what will be the total Q dot? The Q dot supplied to the body. So there will be one due to the heat source over the volume. So that becomes dt, and we have here rho into R dVy, isn't it? Where R is the heat rate per unit mass, rate of heat supplied to the body per unit mass. Okay, plus over the surface del dt, we have H dAy. Okay, and if you read the book, you will see that it induces. So this H, just like traction, T is sigma times N, that comes from the tetrahedron argument. This H can also be thought of as a heat flux vector Q dot with N. Okay, where N is the outward normal to dt. So we can now write it as integral over dt rho r dvy plus integral over del t q dot n dAy, where this q is the heat flux vector. So we call it heat flux vector. Is it okay to everyone? I have made a mistake. Can someone point to me what's the mistake? So Manu is asking, does the unit of H equal watt per meter square? Yes, of course. So it's the per unit area, right? Power per unit area. Heat has the same unit as work. We know it now, and it's per unit area. So it's watt per unit meter square. Yeah, watt per meter square. So like I said, this heat flux is coming out of the body. So what will be the total Q dot for the body? It should be with a minus sign, isn't it? So here you'll have a minus sign. Okay, so now for U part, U, what do you think? What should be U? So we can think of it as a integral over the volume of the body of rho times epsilon dVy, where this epsilon is internal energy per unit mass. Okay, it is per unit mass. And this is total internal energy. Okay, what is remaining now? The kinetic energy, that is something we have already seen. It's again integral over the full dt. That's half rho v dot v dvy. Okay. So let's now put them in the first law. So first, so I'll just write it again. Q dot plus W dot is equal to U dot plus K dot. And what we had was, substituting the above forms, we get rho small r dvy minus Q dot n day plus T dot v dvy, sorry, this is B dot v. And on the right hand side, we have ddt of rho epsilon dvy, and then for the kinetic energy part, plus ddt half rho v dot v dvy. Okay. Now, can you guys tell me what's the next step? What is this equal to from the work energy theorem, power form of work energy theorem? What was this equal to? Yes, isn't this equal to the stress power sigma double contraction d dvy plus the change in kinetic energy, rate of change of kinetic energy, right? This is something we saw. So you see that this always holds. The power form of work energy theorem is also holding, and then we are talking of the first law of thermodynamics also. So when you put that, which is by the way from, I'll just write here, power form of work energy theorem, then you can see that the kinetic term is dropping now from the two sides. Okay, now what do you think? What should be done? See, we want to come up with a local form of first law of thermodynamics. This is the global form. Now we want to come up with a local form of first law of thermodynamics. So we have to then move this d by dt inside and convert this into volume integral. Now this is simple because you can directly use the Gauss divergence theorem and write it as volume integral of divergence of Q, isn't it? And whereas this part, that's also something we have seen a lot of time, but let me do it in steps. So this is now d dt, and we make it over d ref and rho dby then becomes rho naught, and here we have epsilon kind of hat, and this is then dvx. Okay, now you bring dt inside dref, and only epsilon hat gets a dot dvx, and then you switch to the again the Eulerian over dt rho epsilon dot dvy. Okay, so what you see is that effectively you are just putting a dot over epsilon, but we had to go in steps anyway. So this is something we have seen. So putting all of them together, then what we have is all of them are now volume integral dt. We have rho r minus divergence of q plus sigma double contraction d. Okay, and from the right hand side we bring it on the left hand side, and it comes to the minus sign minus rho epsilon dot, okay, dvy. So that's equal to 0. So from here you can use the localization argument, right, because it holds for every dt. And then you can say that the integrand must vanish, or what you get is that rho epsilon dot is equal to rho r minus divergence of q plus sigma double contraction d. Okay, so that's the local form of first law of thermodynamics. I'll put it in the red box. Local form of first law of thermodynamics. So this is also kind of local form of conservation of energy. Okay, so this is, by the way, Eulerian form. Can you similarly think of the Lagrangian form? I don't want to do the whole thing again, but we have to again start from here. So if you think of the Lagrangian form, let me write down each of the terms now in Lagrangian form. But we'll do it, briefly. So Q itself is, Q dot is, we saw it above, it was over dt rho small r dvy minus q dot n day. Okay, so the first is quite simple. You can write it as integral over d ref, and here you get rho naught into small r dvx, isn't it? So that's very simple. For the second one, that's not easy. How to do it over del d ref? So to do that, we'll think of just like we were doing that traction thing, and we came up with first pure Kirchhoff kind of quantity. So here again, I'll just put a sketch also. So this is d ref, and that's dt, and let's say this is that small area through which heat flux is going out, and we want to write that in terms of the area in the reference configuration. So the heat flux which is going out, if we denote that by, as we have written here, Q dot N dAy. So this part here is N dAy. Okay. So I want to write this as, some Q naught dot Nx dAx. So this is Ny dAy. I want to write it as some Q naught dot Nx dAx. Okay, where Nx is here, and that's your Ny. What is then Q naught denoting? Q naught is then denoting heat flux vector, and it's actually a referential heat flux vector or Lagrangian heat flux vector. And that's in the bracket, it is actually per unit reference area, because you see it is multiplied with dAx. Okay. So this way we are introducing a new quantity Q naught. We want a Q naught such that this holds. So if that is to hold, we can also find out how is Q naught related to Q. So this is same as Q dot and Ny dAy. We can use Nancy formula, or the one that we have found out, that's det F into F inverse transpose times Nx dAx, isn't it? And this has to be equal to Q naught dot Nx dAx. So that implies, you bring this on the other side, you have det F into F inverse times Q dot with Nx dAx, that's equal to Q naught dot with Nx dAx. And then from here you can find out what is Q naught, right? Just by comparison. So Q naught is simply det F, which is J Jacobian, times F inverse times Q. Okay, so that's the referential heat flux vector. Just like you had first Euler-Kirchhoff stress tensor, we have this referential heat flux vector, which is going to act on referential normal Nx. And then it gives you the actual heat flux, the heat that is flowing out, but per unit undeformed area. Okay. Anyway, so we can use that here, and this then becomes minus integral over del d ref Q naught dot Nx dAx. Okay. And then the W part, we have already seen the work energy theorem. Okay, Vikram is saying F inverse transpose. Where exactly F inverse transpose? So we have this F inverse transpose here, which when we bring on the other side, it becomes F inverse. Right? When you bring a matrix on the other side, it becomes a transpose. Anyway, so W dot For W dot, we have already seen the work energy theorem, and what we get here is integral over d ref of P double contraction F dot, isn't it? dvx. Okay, and this part you are already seeing here. It's rho naught epsilon dot dvx, epsilon hat basically. So when you put all of them together, so again you have q dot plus w dot is equal to u dot plus k dot, and you put them all together and finally use the localization argument, and what you will get then is rho naught little r minus Lagrangian divergence, okay, that's with an x dot q naught. Okay, up here was Eulerian divergence. I think I have not written that thing explicitly, but this is Eulerian y y y. Okay, so that's the q dot part, and then you have the other one, which is p double contraction f dot, and that's becoming equal to rho naught epsilon dot. Okay, and if you want to be more clear, then this is actually r hat, and this is also epsilon hat, and here we have epsilon bar, we have r bar, and you know that epsilon hat is a function of x comma t is equal to epsilon bar, and then here you get your deformation map y hat of x comma t comma t. Okay, and likewise for small r also. So it's the same way for small r. So small r hat, which is Lagrangian, so it's a function of x comma t is equal to small r bar of y hat of x comma t comma t. Okay, so that's the Lagrangian form of first law of thermodynamics. So this covers your first law of thermodynamics, and we have to then do what is called the second law of thermodynamics, isn't it? That's another one. And all of you know that second law introduces a new concept, that is entropy. In the first law, we got introduced to a new quantity, which is internal energy, epsilon. In the second law, we'll get introduced to a new quantity, which is entropy. So can someone tell me what is the second law of thermodynamics? There are several forms of second law of thermodynamics. So for a system, what do we say is the second law of thermodynamics? Of course, one is that the total entropy of the universe always increases. The change in entropy of the universe is always greater than equal to 0. So that also gives us a direction for the path that any thermodynamic process will take. Thermodynamics is really important because it can help us in getting constitutive equations. It puts restrictions on the system. Okay, so the Well, as I said, the one form is total entropy of the system always increases, or change in entropy is greater than or equal to 0. Then you can also break it into two parts. So if you say entropy by S, then delta S of universe is greater than or equal to 0. And delta S of the universe, you can write it into two parts, delta S of the system plus delta S of ambience. That's greater than or equal to 0. Okay, where what is ambience? Ambience is universe minus system. So if this is your system, your dt, then everything else, not just the remaining part of the body, but also the ambience of the full body, everything else. So if this is your full body, and see, this is the universe. So this part, that's the ambience, the blue shaded part. Everything other than your current system of observation, that's the ambience. Let's say I write it for the full body. And to introduce this S system, entropy of the system, I'll think of it as an integral over the volume see RT, because I'm thinking over the full body. You can also do it over the just dt. So this then becomes rho eta dvy, where eta is entropy per unit mass, and that's also called a specific entropy. Okay. And of course, we don't know how to characterize this ambience thing. How to characterize the entropy of the ambience. Another way to, look at this second law of thermodynamics, it says that the change in entropy of the system minus the entropy supplied, which we can say as delta S external. So that's greater than or equal to 0. Okay, and now we have to quantify this delta S external. So this is entropy supplied to the system. Therefore, and it is, kind of equal to minus of delta S ambience. So this thing is equal to plus delta S ambience. Because who is supplying? It's the ambience who is supplying. So whatever ambience supplies to the system, the ambience itself will get a minus sign, right? Anyway, so what will be the entropy supplied? And I think you all must have seen that the entropy is directly proportional to the heat, isn't it? The heat that is being supplied. So if you talk of, let us say, delta S dot external, then you get it with a heat rate. And how is heat being supplied? it's through the surface as a way of heat flux, or through the source per unit volume, right, per unit mass that we have. Okay, so this is then, can we say that this will be same as integral over the volume, and we have rho times small r by t dvy, because it is heat by temperature, right? Heat by temperature. And then another one which is with a minus sign now, q dot n by t day. Is that something agreeable to all of you? And by the way, in the book, they use theta for the temperature, so I'll also use the same. So we have a new quantity, theta, denoting temperature. Coming here, then for the system, S dot, okay, so if we want to have the dot form, then we have d dt of over the part of the body dt rho eta dvy minus delta S dot external, okay, so that's minus rho r by theta dvy plus q dot n by theta day. Okay, and this has to be greater than or equal to 0. Okay, that's the second law of thermodynamics for a body. And this is also called Clausius-Duhem inequality. Clausius-Duhem inequality. Obviously, the next thing is now is to bring this d by dt inside and then change this to the volume integral, right? So this is obvious to us now. We have divergence y dot q by theta dvy, and this thing is also obvious to us now. You only get a dot over eta. Okay, so what we have finally is rho times eta dot minus rho small r by theta, after using the localization argument, of course, plus divergence of y dot q by theta. So this is greater than or equal to 0. Okay, so this is the second law of thermodynamics. So I think you guys have to go now. So I'll take it up from here in the next class. Okay, we'll write it in a slightly different form, the second law of thermodynamics.